All right, guys, the last thing we have for conics is exactly what the front of the note card says, the intersection of two graphs. Backside is we're going to do one of two things. Either we're going to graph the two functions and locate intersection points, or we're going to solve algebraically by substitution to find the intersection points. And our answers could be one solution, which I need to figure out what that is, or there could be two solutions. I need to figure out what those are, or there could be no solutions, no intersecting points. All right, guys, so I'm going to show you two examples. One, we're going to look at solving by graphing. Then we're going to do one on the back side, solving algebraically. So we need to be able to look at these graphs here and figure out what we are actually graphing. Well, when I look at the first example, in number one, I see that I have a circle. I have two square terms, and they're both the same number in the front of the square term. So I know that one is a circle. I know that right off the bat here. And then I see this one right here. Well, this is a line because the exponent is raised to the first power, x to the first. Well, now I got to remember how to graph a line. So this front side here is nothing but circles and lines. Okay, so I'm going to graph these, and then we'll take it from there. All right, guys, so my first graph that I have here is obviously a circle, and I know it's centered at the origin because there's no parentheses, and I know r squared is 4, so thus my radius is 2. So we have a circle that looks something like that. The last thing I got to do now is graph that line. All right, luckily for us that this line is already in the form of y equals mx plus b, so all I'm going to do is to plot my y-intercept first. So I went to 2 and put a dot. Wait a minute. Look at there. Awesome. And then my slope is -1, so I'm going to go down 1 and to the right 1. And I'm going to do that again, and look at there. We get lucky. So we have two solutions in this case because I see two intersecting points. All right, so once we identify our intersecting points, I just label my points as what I see. So I have two answers in this case. I have 0, 2 and 2, 0. So this worked out nice where when I plotted my points, I get those solutions. It's not always going to be that nice, but hey, this one is good to go. Well, guys, what I want to do here is I'm going to work out number 6, and I'm going to solve it algebraically per the directions there. But when I do this, I'm going to do it by a method called substitution. Well, I'm not going to deal with anything with the square terms. I'm going to deal with this linear function. And to do substitution, I need to know like what one variable is equal to. Since I have x minus y on the same side, let me keep the x where it's at and move the y over. So this is really x equals positive y plus 2. I'm just going to take that negative y and move it over. So I want to do substitution by getting that, in this example, the x by itself. Now say number 7, since y is the positive 1, then I'm going to move the 2x over and have y by itself over there. All right, now the substitution component comes from this. Since we know x is equal to y plus 2, I'm going to take what x is and I'm going to plug it into x in the actual problem. So I'm going to take all of this and substitute it in for the value of x. So we have the following. So as you can see here, I took the y plus 2 and I just plugged it in for x, and now I end up with this right here. But now we have to go through, and this is the algebra part of it, now I have to go through and multiply all of this stuff, combine like terms. It's going to be wonderful. So as you can see here, that parenthesis squared means I have to write this thing out twice. And then what I want to do is to multiply those two parentheses together, and I get that result here. I bring down the y squared, bring down the equals 34, and then we combine like terms. As you can see now, we're slowly getting there. So I notice that y squared and y squared is 2y squared. Notice the y squareds don't change. And since I'm solving, I want it equal to 0, so I'm going to move the 34 over so it's now in the following quadratic trinomial. And what I hope happens is I can factor to solve. And as you can see here, I'm able to take out a GCF first, which is awesome, and then this trinomial can be factored beautifully. This is amazing stuff. It can be factored nicely to those two parentheses, and now what I need to do is to take my two parentheses and solve. And as you can see here, I take my parenthesis y plus 5, I set it equal to 0, y minus 3, set it equal to 0, and I get two values of y. Well, what does that mean? Well, since we're looking for intersecting points, where do the graphs intersect? So again, notice what we started with. We had a circle, and then we have a linear function. So we have a line intersecting the circle at two locations. The fact that I have two values of y means the graph will cross the circle at two locations. Well, it's going to be something comma negative 5, because y is negative 5, but what is x? I know it's also going to cross something comma 3, because y is 3, but what is the value of x? So now the question is, how do you get those values of x right here? Something to do with these points and maybe using that equation right here. I don't know, just saying.